Hi, my name is Gemma Sahwell. I'm a sophomore at Barnard College. I'm majoring in environmental science and I work at Lamont-Doherty Earth Observatory under the Earth Institute's Research Assistantship Program. I work for McManus and Allison Jacobel, who's a PhD candidate here. And here is the core laboratory. Let me show you around. So here's the entrance. And here's a map where there are dots along where all our samples have been taken from. So every dot on this map represents a core that's been taken. And here is the core lab where we keep all our cores. And here's an example of just a few that we have on display. Lamont owns a research vessel, and essentially how you take a core is that there is a rigged core machine on the research vessel, and you plot where you want to take your sediment core from, and then you drop the core down from the boat, and essentially it just goes down, plops down, and collects sediment. And then when you pull that back up, it's capped, and then it preserves. Let me show you where the core that I work on specifically is. So this is the core refrigerator, where all our cores are kept refrigerated, obviously, to preserve their integrity so that nothing like funky grows in them or messes them up. ML 120817 BC, and essentially it takes up all of these. And these were collected off of Hawaiian Islands in the equatorial Pacific. So there's a lot that we can actually learn from cores and studying cores. What I work on is paleoclimate, so that's basically studying past climate events. I specifically am studying organic carbon within sediments that are collected off of Hawaiian Islands in the equatorial Pacific. So basically collecting cores from there, I've been able to look at calcium carbonate concentrations on a timescale of the past 350,000 years. And so essentially that can tell us what the collection of calcium carbonate and organic carbon looked like during kind of peak glacial cycles and interglacial cycles. So what a glacial cycle is when there's not so much CO2 in the atmosphere, and you don't have as many greenhouse gases such as CO2 being released. So ice core data actually indicates that CO2, carbon dioxide levels, have been very variable over large timescales. And since I study a timescale of the past 350,000 years, it's really important to see how carbon dioxide shifts in the atmosphere. It's really interesting that we see during glacial periods, there's less CO2 recorded in the atmosphere, but a lot of CO2 being taken up by the oceans. So we see peaks of primary productivity or photosynthesis in the ocean at that time, and we record that via sediment collection and measuring the carbon in that sediment. And during interglacial periods, like where we are now in the Holocene, there's a spike in CO2 concentrations in the atmosphere, and so what that means is that there is less productivity relative to during glacial periods.
Hi, I'm Nick, and I work in the core lab at Lamont. Basically, when samples come in here, they come in the form of bulk sediment. So the first thing we do is we weigh out a certain amount of sediment and we put it in a sieve. And those sieves, basically, when you shoot water through them, they collect porins and IRP and all of the interesting stuff. So right now, that's what I'm doing with a bunch of samples. You have to brush them and sort of, you collect the fine fraction down here, and all of your coarse fraction material stays on top.
This is Blanca Alvarez. She also works at Lamont under McManus, and she'll take you through what she does on a day-to-day here at Lamont.
So right now, I'm getting the samples ready to be This is what a normal sample looks like. So there are different steps in the process. The very first step is to weigh out your sample. It comes in like a little packet of mud.
I think I could check. So okay, and I could look and make sure. Yeah. But at least part-time. And then
Freeze dried. It just looks like little packets of mud. You weigh them out to get like the weight of everything together, fine fraction and coarse fraction.
I have a good
You
system.
put them in little bottles
Or you
and
can hand it over to the
wash
next person.
them.
So,
After the washing process, you get two different things. You get sieves that have the coarse fraction, which is greater than 63 micron. You kind of have to let them dry. After these dry, they look like this. And the next step would be to weigh them out. And these are little forams. They're little microfossils that used to be alive, and their shells are left over even after like millions of years. Those bags over there contain a fine fraction. It just kind of settles down, and then you weigh that as well. It just tells you about the ratio between the coarse fraction and like how many shells there are compared to all that. So after it's weighed out, you get a little vial like this. It has different little rocks and forams in it that can tell you different things about the past climate.
And I studied calcium carbonate concentrations for PC17. And so essentially that process is called coulometry, where you look at calcium carbonate within samples going down the pore. So to do that, you would have like a little sample baggie. And that's essentially a sample that's already been powdered down, so it's like a fine powder. And then with a little spatula and a weighing apron, you weigh it out to about 0.5 grams on this scale. And then you put them in little vials that are actuated here. So once you have about 2 of these racks filled, you fill them with DI water. And essentially that's just very, very clean water without any particulate matter in it. And you cap them and put them on this machine. And this is a coulometer. So the way that a coulometer works is that it's hooked up to a gas system, and it goes, gas is pumped out through this needle, or acid is actually pumped out through this needle and collected back out, so that it measures how much CO2 gas is being produced from each sample. And the acid that we use is actually right here. And it runs through a color indicator, so the acid would be blue and mixing the whole time, and it runs for about 2 days for 2 racks. And it's basically just one giant titration reaction. So you see how much acid is necessary to dissolve all the calcium carbonate per sample. And that can show you kind of the concentrations down the pore.